Okay, so let's start the last topic for today's lecture. We won't be able to finish it today, but let's start on projectile motion. And projectile motion is two-dimensional kinematics. It's motion not just in one dimension, not just in positive x, negative x, or forward, backwards, or left and right. It's motion that is left and right as well as perhaps up and down. You got 2 degrees of freedom. Now, in order to talk about this, we need a coordinate system. Now, a little bit of background. We were fully able to describe the motion in one dimension with constant acceleration. We were fully able to describe the motion in one dimension with a constant acceleration using those 5 equations. Okay. However, in 2 dimensions, those 5 equations aren't necessarily good enough, right? Now they're all vectors. So if you have a 2-dimensional vector, maybe you remember from grade 12, calculus and vectors, adding multiple vectors that are not necessarily parallel to each other is a bit of a nightmare. In grade 12 calculus and vectors, when you do tip to tail, tip to tail, tip to tail, you have to form a triangle, and they teach you to use cosine law and sine law to solve for the vector addition. It's really super annoying. So there's a better way to do it, really, is I guess what I'm saying. So now that we've extended our analysis into 2 dimensions, that's what we need to formalize. We need to take our one-dimensional equations and expand them just a little bit and figure out how to analyze 2-dimensional motion. So in order to do that, you might remember from either high school physics or grade 12 calculus and vectors, we use components. We use vector components. So I guess before we explicitly talk about this, I have a very easy example for you. So here, does the displacement of an object depend on the specific location of the coordinate system? Hold on, is there a, oh, there we go. This is what I want. So let's start a poll. Relaunch poll, continue, there we go. Okay, so let's do this. Does the displacement of an object depend on the specific location of what I call to be 0, 0, the origin? So, I can call UTM the origin. Does the displacement between any 2 points depend on the location of the origin? And we got 70, 80 people. 100 people. Oh, we're getting there. Ooh, the results are kind of really interesting. Ooh, I love this. Okay, there's about 117 people. I think we had about 120, just over 120 last time, so I'm probably gonna stop it soon. Okay, 124, so I'm gonna end it and share the results. So this is actually really interesting. This is why I have these sorts of questions, because some things that I assume are clear to me, obviously aren't always clear to everyone else. So this is why I have these types of questions, because it's really good to sort of flesh out these misconceptions. So it's about a 50-50 split, I would say. So half of you, well, 43% of you said yes, and 53% of you said no. So let's kind of delve into this a little bit. That tells me we have to review this before we go much further. So I'm going to insert some space, and we can talk about it a little bit. Actually, let me make this a little bit smaller as well. There we go. So let me draw a sample coordinate system for you. And I'm going to call this the origin, right? Let's call that 0, 0. So the question is, does the displacement of an object depend on where the origin is? So let me draw 2 points. Let's say point 1 and let's say point 2. Two different points. And I want to know the displacement of the object when it travels from point 1 to point 2. So like, let's say the object travels along that wavy path, okay? I'm not talking about distance. Okay, this is the distance traveled, does not necessarily the displacement traveled. I'm only talking about displacement. So the displacement would be the straight line distance between P1 and P2. So this would be the displacement, d vector. So the way you would do this using vectors is you would draw vector d2 and you would draw vector d1, and to find the displacement you would simply say d2 vector minus d1 vector, and drawing this is going to be a little bit hard. So this is going to be, let's say, d2, and we add the negative of d1. We're going to go this way. So this is going to be d2 minus d1. So this is going to be d2. This is going to be negative d1. So there's your vector drawing, tip to tail. All right. So let's change the coordinate system a little bit, and let's see if that changes kind of, I'm going to draw the coordinate system up here now. So there's my origin. I've moved it, and but I'm going to draw the points in exactly the same place as before. So let's redo the calculation. We've got a different origin now, but so we're going to have different displacement vectors. We're going to have displacement 1 over here. We're going to have displacement 2 over here. And if we want to know the net displacement, we say d2 minus d1. So if I had to draw my vector diagram for this one, it would be, let's see here, d2. And we add that to negative, oh, I think I need to move this. I think I drew it a little bit too close. Let's move it over here. Okay, so there's my d2, and I probably need to move this writing as well. Oop. d2 vector, okay, and I'm adding that to the negative d1 vector. So d1 usually comes out this way. That's positive d1. Negative d1 would be up over here. That's negative d1. So I'm doing d2 plus negative d1, so it's tip to tail. And then this would be my d2 minus d1. Now you see in both cases that my d2 minus d1 is the same. So that's like more of a mathematical sort of demonstration. Another way to think about it is the distance between my house and UTM is just the distance between my house and UTM. It doesn't matter whether I call Ottawa 0 or Kingston 0 or my house 0 or UTM 0. The distance between 2 points is not a function of what we define to be 0. So so the answer there is no. The coordinate system does not impact the displacement at all. Now, the displacement may not be a function of the coordinate system, but location is 100% a function of the coordinate system. You know, if I say, you know, I live, you know, 1 meter, you know, 1 meter to the right of of this tree. Well, yeah, all of a sudden, if I choose UTM, I don't live 1 meter away from the tree beside my house. I live 15 kilometers away from UTM. So location is definitely a function of what I choose to be my point of reference, but displacement is not. So this one, instead of polling everybody, I think I'm just going to talk about it. So if each component of a vector is doubled, what happens to the angle of that vector? So if we think about this, let me make this a little bit smaller. So if I were to draw, you know, a standard XY origin or axis, and I just draw some vector v, and I say, let's double it. Okay, if I double both the x and the y, then all of a sudden, this vector is twice as long as before. Well, what does that do to the angle? And as long as you double each component with the same scaling factor, it should not change the angle at all. So the angle should be unchanged. It does not change. Oh, I, for some reason, doubled that slide. I'm not sure why. So here's another vectors question for you, because it's important that we make sure we have a solid understanding of vectors. This one I think I will do a poll with. So I'm going to bring up the poll. Polls, relaunch poll. Okay, so I'll read the question. The poll should be live on your end. If two vectors are given such that the sum is 0, a plus b equals 0, what can you say about the magnitude and direction of vectors a and b? Same magnitude, any direction, a. B, same magnitude, same direction. C, different magnitude, but must be in the same direction. D, same magnitude, opposite directions. E, different magnitudes, opposite directions. Okay, not everyone has voted yet, but I think I'm going to end it now because the answer is fairly obvious there. 96% of you are voted D, so I think we're right on the right page there. I think we can move on. Okay, so now our task is to extend the 1D equations that we have. Oh, sorry, I didn't talk about what I wanted to talk about. Coordinate systems, there we go. So I want to loop back before we move on to the next example or the next topic. I want to reiterate kind of coordinate systems. Why are coordinate systems an important topic when we study multiple dimensions of motion, not just one dimension? You'll notice that there's something that everything has in common in this slide here. It's specifically everything is at a 90-degree angle. There's that mathematical symbol for 90 degrees. We get that little, corner there. This is the very famous right-hand rule in physics. Notice when you have the right-hand rule in physics, you hold all of your fingers at 90 degrees. So your thumb and index finger are 90 degrees. Your index finger and middle finger are at 90 degrees in both directions as well. So coordinate systems are usually, if they're invented properly, orthogonal. Everything's at 90 degrees to one another. And the reason we do this is quite simply because, and I have to scroll, my apologies. The reason we do this is because if you take a step in the x direction, you want that to be independent from the step in the y direction. So that's what we're going to be mostly focusing on, tomorrow when we have some time, because we're kind of running out of time now. So we're going to kind of pick up tomorrow with talking about why independence with coordinate systems is good. But before I let you go, I want to sort of show your brain, that way you can let it sit overnight and think about it. I want to show you kind of how we're using vectors to extend our equations. So, everything now is a vector in multiple dimensions of space, not just one dimension of space. So now we have to add cosines and sines. So things like, if I have a velocity vector v, then I now have an x direction and I now have a y direction. So I want to know, I got to break down my components with a certain theta. So I say how much of my velocity vector is in the x direction. So my velocity in the x direction is v, and the way I've drawn this is going to be v cos theta. And how much of my vector is in the y direction, it's going to be v sine theta. So that's kind of where the first two equations are coming in. Let's assume we give you the components. We give you the x velocity. We give you the y velocity. What's the net velocity? Well, that's just the Pythagorean theorem. If you're given the x direction and you're given the y direction, then you just use Pythagorean theorem. You can add the sums of the squares of the side lengths to get the hypotenuse. So that's the 31 there. And then there's some notation issues. Delta D in the x direction, the displacement in the x direction, is often referred to in some textbooks by the range, sometimes capital R. Delta D in the y direction, well, that's the displacement vertically in the y direction. Sometimes that's referred to as the change in height or just height. Acceleration in the x direction, most of the time when you're dealing with projectiles is going to be 0 because there is no force in the x direction, but there is an acceleration in the y direction, gravity. Gravity is pulling us down, so we use little g for gravity, g for gravity. And the last thing I want to mention there, before I let you go, is time. The time it takes in the x direction is going to be the same time as it is for the y direction. And I'm noticing here as I'm looking at this, I have a typo on the slide. It says tx equals t. I meant it to say tx equals ty equals to t. So time is the variable that couples the x direction and y direction. Okay, so tomorrow we're going to kind of pick up from where we left off. We're going to finish the notion of independence of coordinate systems, why that's important. We're going to do some examples with two-dimensional motion on the board here, and then whatever time we have left, we're going to go back and we're going to do some more one-dimensional problems because there are some examples from the previous lecture we haven't finished yet. Okay, thanks for coming out today. I'm going to stop the recording and answer any chat questions that some people may have.